Alright, so we're ready for part B of this example. So we're given different n, p, and this time x is less than or equal to 3, right? So if we're trying to find the probability that x is less than or equal to 3, right, this would mean the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2 plus the probability that x is 3, right? It would include it'll include all of those values, right, from 0 to 3. So we could have 0 successes all the way up to 3 successes and including 3. Right? So using the equation, right, this would be equal to 9 choose 0 times 0.2 to the 0 power times 0.8 to the 9th power, right? So that's the probability that x equals 0, just using that equation. So this would be, the next one would be 9 choose 1, right? 1 success. So that would be 0.2 raised to the 1st power, and then the probability of failing, 0.8 raised to the 8th power, right? There would be 8 failures. And then we need to find the probability that x equals 2, which would be equal to 9 choose 2 times 0.2 raised to the 2 squared, because there's 2 successes, and this would be times 0.8 raised to the 7th, because that means there would be 7 failures. And then we'd have plus, and then probably the x equals 3 would be 9 choose 3 times 0.2 raised to the 3rd power times 0.8 raised to the 6th power, right? Because there'd be 6 failures then. Right, so if you plug that in your calculator, right, or calculate that by hand, you should get 0.91435872, right? So you could use, factorials, use the equation to find a combination, or you can type that directly into a calculator if you have like a graphing or scientific calculator that does combinations. Right? So like just to show you, for example, right, I could do, we had 9, and then we go to the probability menu to get the combination. So we had 9 choose 0, right, and that would be times 0.2 raised to the 0 power times 0.8. Oops. Hang on, I was still in the exponent. There. And then we had 0.8 raised to the 9th power, right? And then I would hit plus, and then we got 9 choose 1, right? So follow the same steps to come over here and get the combination. So 9 choose 1, and then you would type in 0.2 raised to the 1st power, and then 0.8 raised to the 8th power, right? So now we need for 2 successes, right? So we'd hit plus, and then 9 choose 2, times 0.2 quantity squared times 0.8 to the 7th power. Then lastly, probability of getting 3 successes plus, this would be 9 9 choose 3, which would be 0.2 raised to the third power times 0.8 probability of failure raised to the sixth power. Right, hit enter, and that's the value that that I just shown you. Right, so you could do it something like that, or use factorials and do it more by hand, like we did in chapter 5. Right, so now what I want to do is find this using StatCrunch. Right, so here's my StatCrunch calculator. Right, so remember, to get this to pop up, you're going to go to data, stat, calculators, and then binomial. Right, so under the stat menu there's calculators, and then hit binomial for binomial calculator, and we can just type in what we have. Right, so my n value is 9, my p value was 0.2, and then find the probability that we're less than or equal to, so I don't need to change that symbol, right? Less than or equal to 3. And I can hit compute, gives me a nice graph, and it shows me the value, right, which is about 0.914. Right, so this is approximately 0.9144 if we round to 4 decimal spots, right? And using StatCrunch, the probability that x is less than or equal to 3 was also approximately equal to 0.9144, right, from that printout. So then, to be able to find this using the table, there's two different ways that we could do this. This would be equal to the probability that x is 3 plus the probability of 2 plus the probability of 1 plus the probability that x is 0, like we talked about, right? So x less than or equal to 3 means you're going like 3 all the way down to 0, right? So if you're doing this using the table that we were using a little bit ago, so that was this table. Right, let me get rid of this. Right, so now we would be looking at n equals 9, and we're looking at p equals 0.2, so we'd be using this column. And we need to find the probability that x is 0, 1, 2, and 3, right? So that would be these values here. We'd have to add all of those up, right? So we're using the table to find each of those probabilities, but the x is less than or equal to 3 means that we would add those together, right? So this would end up being from the table 0.1762 plus 0.3020 plus 0.3020 plus 0.1342. Right, so I just simply, like I said, we added those numbers together, right? So if you add those up, that gives you 0.9144, right, which is what we were after, right? So that's one way to do this, right? Now, if you don't feel like adding up all those values together, that's where table 4 can be helpful. Table 4 is what we call like a cumulative probability. So if I insert this handout, so this is in the textbook, but I took this page from the textbook. So this is page A8 in the textbook, so appendix A, page 8 in that appendix. This is in table 4. Table 4 is what we call cumulative probabilities. So this works similar to table 3, right? It looks very similar. The difference is, so let me find this one, right? So for this one we had n equals 9, and we had a p-value of 0.2, right? So we're looking at, this column, and what we're trying to find is the probability that x is less than or equal to 3, right? That's what we want to find. So if I look at this 3 row, the row with labeled 3, notice what I get in that spot is the answer that we got using the equation and also StatCrunch, right? 0.9144, right? So these are called cumulative probabilities. So what these numbers represent when you find a particular x value is it's taking that x value and adding up all the ones before it as well, right? So like if you were to find, for example, this value here under the 6, right? That would represent that number, that 0.9997 value, that represents the probability that x is less than or equal to 6, right? So these are all going to be x less than or equal the number that you find over here, right? Where in table 3, it's x equals the number, right? That's table 3. So table 4, instead of equals, it's less than or equal to, right? So you just want to understand that distinction, so that way when you find those numbers in the table, you don't accidentally do the incorrect thing, right? And it makes sense too, right? Because if I were to add all these up like we did from table 3, this would be over 1, right? And that's not possible. And notice, when the x value matches n, we get 1s all the way across, right, in the table. So I'm circling these in red, right? So when the x value matches the n value, we're getting 1s all the way across, right? And of course that would be true, right? Because you're adding up all the probabilities and all before it, and there's nothing after, so the probability has to equal to 1, right? All right, so then part C, we have another example. So we have n equals 7, p equals 0.5, and x is greater than 3, right? So the probability that x is greater than 3, this is equal to the probability that x equals 4 plus the probability that x equals 5 plus the probability that x equals 6 plus the probability that x equals 7, right? We stop here because there's only 7 trials, 7 possibilities, right? And notice it's greater than 3, not greater than or equal to 3. So you got to pay attention to that. So we don't include x equals 3 in this, right? So that's an important distinction. So then using the equation, this would be equal to 7 choose 4 times 0.5 raised to the 4th power times, and the probability of a failure would also be 0.5, right? So in other words, the probability of failure and success are equal in this case, right? So we get 7 choose 4, 0.5 to the 4th, and this would be 0.5 cubed, and then plus, and then we would have 7 choose 5 times 0.5 raised to the 5th power, and then 0.5 raised to the 2nd power, and then plus 7 choose 6, so that would be 0.5 raised to the 6th power times 0.5 raised to the 1st power. And then lastly, we would have plus 7 choose 7, which would be 0.5 raised to the 7th power times 0.5 raised to the 0th power, which these all added up, we get, you can plug this in your calculator, use the factorial equations. This is going to be equal to 0.5, right? So we can double check this this calculation using the equation, using StatCrunch. So my n value is 7, My p-value is 0.5, and I'm finding x greater than 3. Right? So if I hit compute, here's the graph of this distribution. Right? The area I'm finding is what's in red, and that area is 0.5. Right? That's the probability. Right, so using StatCrunch, we still get that the probability that x is greater than 3 is 0.5. Right? So then to be able to do this using a table, right? So we could do this using either table actually. If I wanted to use this, using table 3, right? The probability that x is greater than 3 would be equal to the probability that x is equal to 4 plus the probability that x equals 5 plus the probability that x equals 6 plus the probability that x equals 7, right? And I could locate each of those in the table like we did before and add those up, and that would give me 0.5, right? If you wanted to do this using table 4, right? To do this, you have to write this a little differently, right? You have to understand that the probability of x greater than 3 is equal to 1 minus the probability that x is less than or equal to 3, right? So that would be a complement of x bigger than 3, right? So if your number is bigger than 3, the opposite of that would be 3 or less, right? So this is using the complement rule. So then you can locate this in table 4, right? And you can take 1 minus that value, which is 0.5, to get 0.5. Right? So let me I can show you in the textbook if you'd like, just to verify that. All right, let me just open up a section in the book. Easier to get to it that way if you have it launched in a tab. Go to the menu, go to Appendix A, right, and we were looking at Table 3. Right, so we were trying to find probability that x is greater than 3, and my n value was 7. Right, so I can use this first page in this table. My p-value was 0.5. Right, so I would be here in this column. So I'd have to add up these values of 4 through 7. Right? So if you add those up, you get 0.5. If I scroll over to table 4, sorry, right, I would look for n equals 7. My probability is 0.5, so I'm here. And then I would scroll down to find x equals 3, which you can see the probability there is 0.5, right? So if I take 1 minus that value, I'm going to get 0.5, right? All right. So now, example 4, we're told that in a recent poll, the Gallup organization found that 45% of adult Americans believe that the overall state of moral values in the United States is poor. Suppose a Suppose a survey of a random sample of 25 adult Americans is conducted in which they are asked to disclose their feelings on the overall state of moral values, right? So we want to be able to label what's given. This 0.45 value would be your P, right? That's the probability of success, right? And you want to pay close attention because sometimes the percent given is not a success, it's the failure rate, right? So you'd have to take 1 minus that value to find the P value, right? So you just want to pay attention to that. So of course 1 minus P would be equal to 0.55, right? That would be the failure rate. And this 25 number, that's your N value, right? That's the number of trials that we're doing. So part A says that we want to find and interpret the probability that exactly 15 of those surveyed feel the state of morals is poor, right? So we're trying to find what's the probability that X equals 15. All right, so I'm going to do this just using StatCrunch. Right, so my N value is 25, my P value is 0.45, and I'm trying to find when X equals 15. Right, so we get that value there from StatCrunch, 0.0520, right, if we go to 4 decimal spots. Right, so this is 0.0520, right, using StatCrunch. So then what we're asked to do is interpret that value, right? So let's make sense of what that number represents. Right, so I'm going to just go ahead and type this. So let me get everything set up. Right, so we could say, I'm going to use 100 trials, so I'm thinking of this number as 0.05, right, because that would be to the nearest hundredth. So we could say in 100 trials of this study, we expect about 5 trials to result in exactly 15 adult Americans who feel the state of morals is poor. Right? So again, I'm thinking of this as being approximately equal to 0.05, which is equal to 5 out of 100. Right? So we did 100 trials of this study. About 5 of them would result in exactly 15 people who feel the state of morals is poor, right? So 15 out of the 25 people, right? So then part B says find and interpret the probability that no more than 10 of those surveyed feel the state of morals is poor, right? So you want to be able to interpret the no more than 10, right? No more than 10 means that we can't have like 11, 12, 13, etc., right? So what that means is we're trying to find the probability that X is less than or equal to 10, right? That's what the no more than 10 would represent. So if I go back to StatCrunch, I just need to change this to 10 and this to less than or equal to, hit compute, I can get that value. So it's 0.38. Right, so this equals 0.38, roughly. So then to interpret this, I can use, similar sentence structure that I did before. Hang on. Right, so I'm just gonna move this down here, right, and just change some of the wording. So in 100 trials of the study, we expect about, so instead of 5, it would be 38, right? Because it's about, 0.38 is equal to 38 out of 100, right? So in 100 trials, we would expect about 38 to result in no more than 10. Right? No more than 10 adult Americans who feel the state of morals is poor. Right? So then part C, we want to find and interpret the probability that 13 or 14 believe the state of morals is poor. Right? So this would be the probability that x equals 13 or x equals 14. Right? And so we can use the addition rule here to know that this would mean the probability that x equals 13 plus the probability that x equals 14. Right, because these would be mutually exclusive. Right. Also, this would mean the same thing as the probability that x is in between 13 and 14, right, including those endpoints. Right, so that would just mean the numbers 13 to 14. So that covers like a range of values. So the nice thing about StatCrunch is you can find those in-between values as well. If I hit between, I can change my values here to be in between 13 and 14. And I think I have the n and p values correct, right? So I can hit compute, and it finds that for me, right? So if I hit this, between button, notice I have x in between, and then I fill in the two numbers in between. So that's a nice feature, and you can see in the graph, right, it's highlighting, x equals 13 and 14 in red. So this value is equal to 0.21, roughly. Right? So then I'll just drag this sentence down here again. We need to change a few things. So in 100 trials, we would expect about 21 trials to result in, we just need to change this to 13 or 14. 13 or 14. Right, 13 or 14 adult Americans who feel the state of morals is poor. Right? Alright, so then part D, it says, would it be unusual to find 20 or more adult Americans who believe the overall state of moral values in the United States? Right? And why? So remember, we think something's unusual if a probability is less than 0.05. Right? So what we're trying to find is what's the probability that 20 or more, so that would be x greater than 20, is. We want to know what this value is. If this is less than 0.05, then it's unusual. Right? If it's greater than 0.05, it's not unusual. In other words, it's usual. Right? So we can find what that probability is using StatCrunch pretty easy, right? So I need to switch back to the standard calculator. I want to change this to x greater than or equal to and type in 20. Hit compute, right? And my n and p value is the same as before, right? So notice this value is really small, right? So we ended up with 0. And it's 1, 2, 3 zeros. 1, 2, 3, and then 3, 8. Right? If I just round to 5 decimal spots. Right? So that's clearly less than 0.05. Right? It's a really small number. So that's why. So it's unusual. So yes, it would be unusual, since the probability of x greater than or equal to 20 is equal to 0.00038, which is less than 0.05. right? All right, so then the next page here, we're looking at objective 3, which is to compute the mean and standard deviation of a binomial random variable, right? So I have here the equations to calculate this. So to find the mean or expected value in a standard deviation of a binomial random variable, we have the following equations, right? So we have mu equals np, and the standard deviation is equal to the square root of n times p times 1 minus p. So we can find those values using those formulas, right? So let's practice this. So in this example, it's example 5. It says in March of 1995, the Harris poll reported that 80% of parents spank their children. Suppose a recent poll of 1,030 adult Americans with children find that 781 indicated that they spank their children. If we assume that parents' attitude towards spanking has not changed since 1995, how many of the 1,030 parents surveyed would we expect to spank? Do the results of the survey suggest that the parents' attitude towards spanking may have changed since 1995? Right? So let's take a look at this, right? So this 80%, and this should be of, right? This 80% value is your P. Right? That's the probability of success, right? Where in this case, success is parents spank their children, right? And then this 1,030 value, this is your N. Right? So N equals 1,030 and P equals 0.08, or 0.8, sorry, not 0.08. All right. So let's first find the mean, right? So the mean of x is equal to the expected value, right? So this is equal to n times p, which would be equal to 1,030 times 0.8, which is equal to 824, right? That's the mean. So we would expect, to have somewhere around 824 out of 1,030 parents to spank their children, right? So if a parent's attitude may have changed, we can think of this as like having something that's unusual, right? So, what we would expect to happen would be that we would be within 2 standard deviations of the mean, right? So so inside of here would be the number of parents that spank their children, right? So x. So we would expect to have a number in between the mean plus 2 standard deviations, or the mean minus 2 standard deviations. Right? So what we have, what we're given though, is that in the survey that we did, we had the value 781 indicated that they spanked their parents. So 781 is less than the mean, right? So it's going to be somewhere on this part, right? It's not going to be bigger than the mean, right? So in other words, if we draw a picture, we're going to find out on the next page that if your n value is really large, we can expect a binomial distribution to follow the empirical rule. So remember what the empirical rule says, right, is we're going to have like a normal distribution, a unimodal symmetrical distribution shape. Right in the center is going to be my mean, which in this case we just found that to be 824. Right? And then over here is going to be my mean minus 2 standard deviations. And then over here we would have the mean of x plus 2 standard deviations. Oops. And the percentage of data in between here is 95%, right, using the empirical rule. So if you're within 2 standard deviations, remember that there's 95% of the data, right? So that means outside of here, there's a total of 5% there. So there would be 0.025% on this tail and 0.025% on this tail. Right, because there's 0.05% total, right? So 1 minus 95% is 5%, right? Or actually, I shouldn't use the percent symbols, right? Because I wrote that as a decimal. Those are different, right? 0.05 is 5%. 0.025 is 2.5%, right? So what I should have done is said this is equal to 2.5%. This is equal to 2.5%. And this is equal to 5%, right? So again, what we're thinking about is if something is here or here, that is unusual. If it falls in here, then this would be usual, right? This is not a suspect, right? It's not crazy. So that's what we're trying to find, right? So I picked a value, or I didn't pick a value, I sampled and found 781. So that's to the left, over here somewhere, right? So 781 is going to be somewhere over here to the left of the mean. So what I need to figure out is it going to be here or here, right? In other words, is it going to be to the left or right of the mean minus 2 standard deviations, right? I don't know. That's what I need to figure out. So let me come off to the side here. So what we need to find is I need to calculate the standard deviation of my random variable x. So this is equal to the square root of n times p times 1 minus p. So remember that n is 1030, p is 0.8, and 1 minus p will go here. Right? In other words, this is equal to the square root of 1030 times 0.8 times 0.2. Right? So this comes out to be approximately equal to 12.8. Right? So if I take the mean minus 2 standard deviations, that would be equal to 824 minus 2 times 12.8, which is equal to 798.4, right? So basically what I found, if we go back to my picture, is that this number here is 798.4, 0.4. Right? So finding 781 parents that spanked, that's going to be over here somewhere, which is to the left of that cutoff value, right? So this would be unusual, right? It's in that range where it's unusual. Right? So we could say that the results suggest that parents' attitudes have changed since 781 is less than the mean minus 2 standard deviations, which was 784.4. Right, so in other words, that value, finding 781, is lower than we would expect to happen. So the question is, the mean must have shifted, right? Let me draw what I'm suggesting here, right, to help this make a little more sense. Right, so here's our normal distribution. In the center is my mean, which in this case, for this problem, was 824. Right? And then what I found is this value, which was the mean minus 2 standard deviations, which is equal to 798.4. Right, that's what this value is here. And this would correlate to a z-score of negative 2. Right, so this would also be a z-score of negative 2, right, because we're 2 standard deviations to the left of the mean, right? So don't forget about z-scores. We'll be using those in the near future again, right? So what we have is I have a value or a sample where 781 indicated that they spank, right? So that value is going to be over here, right? So remember, if I'm in between this 95% of the data, in between 2 standard deviations, this is usual, right? This is okay, right? But this value is unusual, since it's less than, it's in that that outside 5%, right? So what it seems is this mean that's right at 824. It's likely that maybe this shifted over, where you get a new curve that has a mean closer to this value. So that way, it puts it where it's within 2 standard deviations, right? So maybe, whoops, didn't mean to erase. Right, so then I'll draw this in blue. So maybe, here and here are now my 95% interval, right, or within 2 standard deviations. So now this 781 value is inside of there, and that's something that we would expect to happen, right? So it suggests that maybe that's true, maybe it's not, right? So and what we're trying to do with this example, and what we've been talking about with this unusual bit, is we're one thing I really like about this text is it's trying to introduce you the hardest part of the course, which is hypothesis testing, which is the very last thing that we'll do. Right? So thinking about when things are unusual, and if things may have changed, right? So then objective 4 is titled graph or a binomial probability distribution, right? So if you want to graph a binomial probability distribution, you first need to find the probabilities for each possible value, right? So in other words, you need to create a binomial probability distribution, a table. And then you're just going to graph it just like we did in section 6.1, right? So I have some examples here out of the book that I just want to talk about. So like in part A, it says graph the binomial distribution with n equals 10, p equals 0.2, right? So what we have to do is get this table right here, where it just takes all the x values, 0, 1, 2, 3, all the way up to 10, and we have to calculate each of those probabilities using the equation or StatCrunch or a table that we've been doing. And then once you have all those values filled in, then you can make the graph, right? Just like this. So that's the graph of this, right? And what we want to do is comment on the shape. So you want to notice that this distribution is skewed to the right, right? Because it looks something like that, right? So it looks something like that with a long tail on the right. All right, and something I want to point out is that in this one, the p-value is 0.2, right? So then in part B, we have an n value of 10, a p-value of 0.5, and we get these probabilities, right, calculating it 0 to 10, and we get this shape for the graph, and it looks to be symmetrical, right? So p equals 0.5, and it appeared to be symmetrical, right? So far, we had p equals 0.2, and it looks to be right skewed, right? So then in part C, it says table, we have this table that shows the probability distribution for n equals 10 and p equals 0.8. Right, so we have n equals 10 in all of these, right? Then we get, looks to be this left skew distribution shape, right? So after looking at this example, right, it says based on the results of example 7, we conclude that the binomial probability distribution is skewed right if the probability, if p is less than 0.5, symmetric and approximately bell shape if p equals 0.5, and skewed if p is greater than 0.5, right? So we're just looking at, notice this, p equals 0.8 is greater than 0.5, and it looks to be skewed left, right? When p equals 0.5, it looked to be symmetrical. When p was equal to 0.2, it looks to be right skewed, right? And in all of these, all we changed was the p-value. We left n equals 10. We left that constant, right? So we could compare. And also, since p equals 0.8 and point equals 0.2, since those both add to equal 1, something to notice is those are mirror images of each other, right? So it's like we just flipped, like 0 became 10 and 1 became 9 and so forth, right? That's what happened here, right? They just kind of flipped. So we have seen the role that p plays in the shape of the binomial distribution, but what role does n play, right? So in this case, we left n be the same and changed the p-values, and that impacted the shape. But we want to think about, what does n play? So figure 12 shows the graph of 3 binomial probability distributions drawn in StatCrunch. So in the first graph here, n equals 10, and p equals 0.2, right? In this next one, we have n equals 30, right? So here, this is n equals 10, p equals 0.2. And this one, n equals 30, and p equals 0.2. And here, we have n equals 70, but p equals 0.2, right? So in other words, we left p be the same, but 0.2 all the way across, right? And we have various n values. And what you want to notice is when n equals 10, this looks to be right skew like we would expect. But as n gets large, notice that in the last one, it looks more and more symmetrical, right? Both of these look more and more symmetrical. So this first one is skewed right. This one is, slightly skewed, right? And this one looks, to be bell-shaped, right? So what this phenomenon means, so if for a fixed value p, as the number of trials n in a binomial experiment increases, the probability distribution of the random variable capital X becomes bell-shaped, right? So as a rule of thumb, we use this as a rule of thumb. If we take n times p times 1 minus p, if that is greater than or equal to 10, then the probability distribution will be approximately bell-shaped. Right? So if this is true, then the probability distribution will be approximately bell-shaped. So this result allows us to use the empirical rule to identify unusual observations in a binomial experiment, right? So remember, that's the 68, 95, 99.7 rule, right? So the empirical rule, right, is the 95, 90, 68, 95, 99.7 rule, right? That we've talked about in the past, right? So just as a quick refresher, right, what that says is if we have a bell-shaped distribution, right, a unimodal symmetrical distribution, then in the center we're going to have the mean. So I could draw this just being I could draw an axis right below with the z-scores, right? So remember, the z-score for when you're at the mean, the z-score is 0, right? And then if you go the mean plus 1 standard deviation, then that is a z-score of 1. And then if you go 2 standard deviations to the right, that's a z-score of 2. And then if you go 3 standard deviations to the right, that's a z-score of 3, right? And then we could go to the left a standard deviation at a time, right? So the mean minus a standard deviation matches up with a z-score of -1. The mean minus 2 standard deviations matches up with a z-score of -2. And the mean minus 3 standard deviations matches up with a z-score of -3, right? So what this empirical rule says is that if you're within 1 standard deviation, right, we get 68% of the data we would expect to be there. If you're within 2 standard deviations, this value is 95%. And then lastly, if you're within 3 standard deviations, the percent of the data in here would be, approximately 99.7%. Right? So that rule will still apply. Right? So, in this other words part, right, it's just saying that, if we have this where n times p times 1 minus p is greater than or equal to 10, then the interval, the mean minus 2 standard deviations, all the way up to the mean plus 2 standard deviations represents the usual observations. And then if something's outside of these, we consider them to be unusual. All right. So I have one example left. Example 6. So it says a binomial probability experiment is conducted with the given parameters n equals 6 and p equals 0.3. So in part A, we want to construct a binomial probability distribution, right? So in other words, I want to fill in this table for the possible x values, right? So x could be 0, 1, 2, 3, 4, 5, and 6, right, are the possibilities. So I need to calculate those various probabilities, right? So I'm going to use StatCrunch to help me calculate those. Right? So my n value in this case is 6. My p value is 0.3. And I want this to be equals. And then the first thing I want is to calculate x equals 0, right? So this would be 0.1176. So I'm going to round these to 4 decimal places, right? So then I could do x equals 1. I get 0.3 0.3025. And then I could do x equals 2. We get 0.3241, right? And then you do x equals 3. We get 0.1852. And then x equals 4. Get 0.0595. X equals 5. We get 0.0102. And then for x equals 6, I get 0.0007. Right? So then in part B, we're asked to compute the mean and standard deviation of the random variables using the methods from 6.1. Right? So from 6.1, the mean of a random variable x, discrete random variable, is equal to the sum of the x values times their probabilities. Right? We'd have to add all those up, right? So this would be, 0 times 0.1176. Oops, not need just two ones, not 3. There. Then we'd have plus, and then 1 times 0.3025, right? And then plus 2 times 0.3241, plus 3 times 0.1852, plus 4 times 0.0595, plus 5 times 0.0102, and then plus 6 times 0.0007. Right, we want to multiply those and add those up, right? If you do that, put that in your calculator, you should get 1.8. Right? So then the standard deviation, right, from section 6.1, if we have just a binomial probability distribution, discrete, right? If you have just a discrete probability distribution in general, the standard deviation is found by taking the square root of sigma x squared times p of x, and then you're going to minus the mean of x squared, right? So, using this equation, I already know what mean of x is, right? I found that just moments ago, right? So this is equal to the square root of sigma x squared times p of x minus, so I can fill that in, we found that to be 1.8, right? So this would be minus 1.8 quantity squared. So what I'm missing is this part I'm highlighting in green. I need to find that, right? So if I come off to the side, right, what I'm trying to compute is sigma x squared times probability of x. I need to calculate this part. Right? So this would be equal to, so we would have 0 squared times 0.1176 plus 1 squared times 0.3025, right? Plus, so it looks like the mean, except we're squaring the x value first, right? So this would be 2 squared times 0.3241 plus 3 squared times 0.1852 plus, and then 4 squared times 0.0595 plus 5 squared times 0.0102 plus 6 squared times 0.0007. Right? So we need to figure out what that value is. Right, so this value comes out to be equal to 4.4979. Right, so if I come back over here to the equation, right, I figured out what that value I highlighted in green is, right? So this is going to be equal to the square root of 4.4979 minus 1.8 quantity squared. So this comes out to be approximately, if I just round to 1 decimal place, 1.1. Right, so the standard deviation is 1.1, the mean is 1.8. Right, so that was using the mean or using the methods from section 6.1. Right, just for some more practice. So then in part C, now we're using the equations in this section. So a nice thing about this is they're a lot easier. Right, so remember the mean for a binomial is just n times p, and the standard deviation for a binomial, right, is equal to the square root of n times p times 1 minus p. Right, so in this example, remember that n was equal to 6 and p equals 0.3. Right, so 1 minus p will of course be 0.7. Right, so the mean would be n times p, or 6 times 0.3, which is 1.8. And the standard deviation, right, would be equal to the square root of 6 times 0.3 times 0.7, which if you put that in your calculator, that equals approximately 1.1. Right, so just like we found. So then the next part, part D, says to draw a graph of the probability distribution and comment on its shape. Right, so if you're graphing this by hand, right, we need to have an x-axis, and this would be the probability of x happening, right? So I'm going to go up by 0.05 in the probabilities. Right, and then along the x's, we need to go up to 6. Right, and this, of course, here would be x equals 0. So then we just need to look at that table, that we made in part A and graph those. Right, so so the first for 0 is 0.1176. Right, so somewhere around here. Right. Oops, let me undo whatever I just did. There. Right, so remember, you just draw a dot and draw a line straight down. Right, so then for 1, the probability was about 0.3. Right, for x equals 2, the probability was about 3.32. For x equals 3, the probability was about 1852, right? 0.18. Whoops. For 4, the probability was about 0.05. For 5, it was about 0.1. And for 6, it was really tiny, right? So it was practically 0, right? So just have a really little dot, right? And we're supposed to comment on its shape. So notice the shape, looks to be skewed right. Right? And if we come over to StatCrunch, right, when we were finding these, you can get the graph here. Right, as well, right? So we had n equals 6, p equals 0.3, and you can see that's what the graph looked like. Right? All right, so that's all I have for this section. Make sure you let me know if you have any questions. Thanks.